In this problem, we learn a little bit about the annual sales of swimming pools for a particular company. We are given a function, n of t equals t times the square root of 4 minus t, and we're told that n is the number of swimming pools in thousands sold nationally, where t is the number of months since the beginning of the year. All right. We're asked to calculate two numbers, n of 5 and n prime of 5, and we're asked to interpret these values. So we need to calculate two numbers and then talk about what those numbers represent. I think I'll start with actually thinking about what they represent, and then I'll do the calculations. N of 5 then means the t value is 5, so 5 months since the beginning of the year is the point in time we're interested in. So time 0 would be 0 months, that would be the very beginning of the year. Time 1 would be 1 month, so that would be where, let's see, time 1 would be 1 month in. This would be the end of January, beginning of February, right on that boundary. And if you step forward here, that means time t equal 5 is end of May, start of June, right on that boundary. All right. So they're interested in what's going on right near the end of May, start of June, beginning of June. And they want to know how many pools have been sold up to that point in time, and the derivative. Now, what would the derivative measure? The units on a derivative are the place I would start when I'm looking for this interpretation. They follow a very simple pattern. The derivative, again, is measuring slopes, which is rise over run. That's the change in the function values divided by the change in the variable. So the units on a derivative is always the units on the function divided by the units on the variable. So in this case, the units on n prime will be thousands of pools per month. So this is telling us not how many pools are sold, but what rate that sales figure is changing. So n prime of 5 is going to be the number of pools per month in thousands here, number of pools in thousands per month, that the sales is increasing or decreasing. All right. Since it's total sales, total root of 9, which is, I guess, 3, and 5 times 3 is 15. And the units on this would be thousands of pools. So again, the interpretation is that by the end of May, 15,000 pools are sold. All right, that's the first part of it. So I have now a pretty good picture. By the end of the 5th month, we've sold 15,000 pools. Chances are throughout the month of June we'll sell more pools, so the total number of pools should be increasing. The question is how fast. The derivative will tell us that. To find the derivative, I'm going to rewrite the function once just to put it in a little more calc-friendly form. Radicals don't really fit in with the way we describe many of our derivative rules, so I'm going to use a 1/2 exponent instead. And when I do that, I see a product right here in between the t and the 4 plus t to the 1/2. This means I'm going to approach this derivative using the product rule. And before I carry out that work, let's think about the terms within the product. The derivative of the t is no big deal. The derivative of t is 1. So that piece is not going to be difficult. This other portion cannot be simplified in any way. The 1/2 can't be distributed onto the 4 or the t. That simply is bad algebra. I can't do that. So I'm going to need a chain rule on this piece. So when I differentiate this, I'll use the generalized power rule form of the chain rule. Bring the 1/2 down, leave what's inside alone, reduce the exponent by 1, and multiply by the derivative of the inside. The derivative of the inside is not too bad. It's just the derivative of 4 plus t, which is 1. So I'm starting to get a picture for the roadmap on this derivative now. Product rule with a chain on the second piece. And then just thinking about the algebra cleanup that would come afterwards, the fact that I'm chaining on a portion of my product rule tells me that if I want to simplify my answer, I should expect to factor out the quantity I chained on, which means, in this particular case, I think I'll be able to factor out some 4 plus t's. So just keep that in mind as we go forward, and we'll see if that happens. So the product rule again, derivative of the first, which is the derivative of the t, is 1, leaving the second alone, plus the first, so leave the t alone, times the derivative of the second. So here comes my chain rule on the second piece. Bring the 1/2 down, leave what's inside alone, reduce the exponent by 1, so 1 less than 1/2 is negative 1/2, and then multiply by the derivative of the inside, which is simply 1. So I have finished the calc step, and I just want to clean this up a little bit. For this particular problem, it's not imperative that I clean it up. I want a single number here, so I could simply place a 5 in here for t and work our way through this. But typically, when you're analyzing a function, you're going to want to know the derivative at more than one place. So it's worth your while, in general, to clean this up. So I'm going to go ahead and factor across this plus sign anything that's common. And again, I see that 4 plus t is predicted, so some 4 plus t's will come out. There's some here and some over here, and you factor out the lower number. I've got a positive 1/2 here and a negative 1/2, so I can pull out a negative 1/2 of these. And then I just see what's left over. I'll multiply by the rest. I don't see anything else that can factor out since this has nothing else in it. If I pull out negative 1/2 from this 1/2, then I'm leaving behind 1. And again, when you first see that, that might be a little bewildering, but you can check your work pretty simply here. If I take 4 plus t to the first and multiply by 4 plus t to the minus 1/2, the exponents, and there's an implied exponent of 1 here, the exponents add, so 1 plus a negative 1/2 would be 1/2. Then here's the plus sign from the product rule. And on the right side, I've pulled out the negative 1/2, so all that's left in here is a 1/2 and a t. Alright. I'm going to clean this up a little bit more here by doing 2 steps. One is cleaning up what's in this square bracket, and the other is getting rid of this negative exponent. This can be confusing. The negative exponent piece just means whatever I've got is in the denominator. So I've got a 4 plus t to the positive 1/2 in the denominator from this first piece. In here I've got a 4, and I've got a t plus 1/2 a t. So that would be 1.5 t's or 3/2 t right here. Alright. So now I'll finish doing the calculation they wanted. They wanted n prime at 5, and that means place a 5 into my formula. So that's 4 plus 3/2 times 5 divided by the square root of 4 plus 5. If you do the calculations on this, then you end up with